This is a Game Boy, and this is what happens when a small population of Game Boys becomes isolated on an island. This is the Pokémon Mini. It's not some cheap Pokémon toy you'd get from Walmart. This is a game console, the work of Nintendo R&D 3, the same team who pioneered the hardware behind the family computer Game Packs, developed classic games like Punch-Out and Star Tropics, then went on to create some of Nintendo's best consoles, the Nintendo 64, the GameCube, the Wii, Wii U, and later took over the 3DS line. So, to a team with this reputation, the Pokémon Mini is basically just a footnote of something they did while working on the GameCube. In fact, the Pokémon Mini was released 2 days before the GameCube in North America, then later released in the world's only other two markets, Japan and Europe, in December and March respectively, well after the GameCube was already on the shelves in both places. Kind of a weird launch time for a new console, but it is a pretty weird console in general. Ignoring the Pokémon branding, this computer is essentially a light version of a Game Boy. I mean a micro Game Boy. I mean a very small Game Boy. It's a portable handheld gaming machine that takes teeny tiny cartridges, has A, B, and C buttons, a motion or shock sensor, an infrared sensor, and rumble feedback. More bells and whistles than the original Game Boy and only $40 US. Successor of the Pocket Pikachu line and uncle to the Pokewalker, it's not that well known of a console. Well, the Pokémon Mini really isn't a canon Nintendo console. But given everything that it is, I think that it can definitely be considered an apocryphal console. Basically, the only thing that separated it from a regular console was respect, and maybe color by 2003, and I guess popularity. But I seriously question why it was never a big hit because the games for the system are so good. Granted, they're all Pokémon mini games or spin-off titles, but not a single one of them feels like shovelware. Pinball, racing, RPGs, party games, Tetris. This console has everything. And since my goal is to program every Nintendo console, I just have to make a game for this system. Opening up the back to take a look at the hardware, there's the vibration motor on the left, then the cartridge slot, C shoulder button, 8KB EEPROM, probably, don't quote me on that, and then what I think is the shock sensor. Then on the front of the PCB is the infrared sensor, button area, and that magic black blob, which in this case houses an Epson S1C88 8-bit single-chip microcomputer. A microcomputer since it contains both the S1C88 CPU core along with the system's 4KB SRAM and 4KB BIOS ROM. That's not a lot of memory even compared to the original Game Boy, but the processor runs at 4 MHz, supports 16-bit instructions, and a whopping 24-bit address bus. So it's fairly competent for such a small package. And on the graphics side of things, it only needs to run a 96 by 64 pixel monochrome display, which the system takes care of through the program rendering chip, which isn't a real chip, but a hardware-level process that halts the CPU to render the frame buffer. Basically a poor man's PPU. Opening up a cartridge, it's pretty simple. Just a ROM chip hooked up to the pads down below. While the S1C88 CPU does support a full 24-bit address bus, the cartridge bus is only 21 bits. So everything from address 200000 onward is just a mirror of previous data. Working backwards, the cartridge memory is directly addressable by the CPU from address 2100 to the end, 1FFFFF. That's about 2 megabytes of ROM data available for game code and graphics. More than reasonable for 2003, as that's about 32 times the size of an average Game Boy ROM. The rest of the memory map is split between the 4 kilobytes of BIOS ROM, 4 kilobytes of RAM, and 1 page of hardware registers. Taking a look at these registers, there are quite a number of them to give full control over this system's unique hardware. Lots of interrupt and counter registers. The S1C88 was meant to be placed in digital watches, so there are a lot of timers in this thing. But to start the system up, I only need to set a few of the registers to the right values so everything functions properly. First though, it helped to be familiar with the S1C88 CPU. This architecture features 4 8-bit A, B, H, and L registers, combined as the B, A, and HL registers for 16-bit operations, the IX and IY 16-bit index registers, along with various other registers for additional support that I'll mention as they become relevant. As far as I'm aware, the S1C88 is not directly related to any other architecture, though Epson's engineers would at least have been familiar with x86, because who wasn't, and the Z80 lines considering their work with MSX computers. So the similarities between those instruction sets and S1C88 assembly is not a coincidence nor a surprise. And while it's technically a CISC architecture, there aren't too many instructions, or at least instruction mnemonics, to keep track of. Load does mostly anything you need it to, with some caveats that are easily worked around. There's the basic arithmetic and bitwise logic instructions. Really, the only mnemonics that threw me off were JRL and JRS for jump relative long and short, and CARL and CARS for relative call long and short. I guess they didn't want to use jump subroutine, as that would probably get confusing. Otherwise, once familiarized with the registers and the special ways you can use them, it's a super basic assembly language. I'll be making use of the S1C88 toolchain as provided by the Pokémon Mini development community on GitHub. Really, I'll just be using the C compiler created by Epson themselves, although I'll just be using it to assemble my assembly code. Though most, if not all of the people in the Pokémon Mini dev community, which has near totally migrated over to the Discord by the way, use C rather than assembly. And given that this console came out in the early 2000s, it's probably a safe bet that the main games were also written in C, but this is right at the point where assembly still could have been used, so that's what I'm gonna go with. By the way, I'm definitely more of an online wiki kind of guy when it comes to development documentation, rather than searching through Discord channels for the answer to some question that CarrotOtaku77 asked back in March of last year. Of course, there is PokemonMini.net, which contains decent hardware documentation, but it isn't as detailed as other development wikis have been. Still, this is where I downloaded the Pokémon Mini emulator, which I'll be using to run the digital ROMs. Back to S1C88 assembly. First, the compiler will only work with assembly files labeled .asm. I tried .s and it just didn't like it, so keep that in mind. Second, I'll globally define the entry point for the program. Then instead of a .data section like you'd see in x86 assembly, I'll define a sector and label it as data and then place that at address 14EO, which places this section right in RAM where it's safe to put programmer-defined variables. Then to add some actual data to this section, I'll write sect and then the section name, and I'll define a variable just for testing right now using ds1 or define storage 1, meaning that this variable will take up 1 byte of RAM. Don't use db or dw here because in this version of assembly those keywords define constants, not variables. Next, I'll create a section for code and place it at address 3000. Which is a little way after RAM ends, but the cartridge header will be placed right after RAM, so I need to space it out a little bit. I used the entry point I defined earlier. This is where the system will jump to when it powers on, so I'll just do a quick system reset here, setting the top page of the IX and IY registers to 0 through the XP and YP registers, then clearing the entirety of RAM using this little loop, using the HL register's indirect addressing properties. Then I'll set up the stack pointer, system control, and base register. This last register here is used for 8-bit absolute addressing, as in the value of BR is used as the top 8 bits of the 16-bit address. So this command sets the byte at address 2070 to the value 0. Between addresses 2000 and 2100 are all these system registers, so 2070 is the audio control register, which should be set to 0 to allow sound and 1 to mute sound. Then there's a bunch of registers for the second counter, 3 general purpose timers, and a 256Hz timer. Real funny to think of making a wristwatch CPU the heart of your console, but I bet it was pretty cheap. I'm not really going to touch the timers, so I'll skip setting up all those registers for now. But I will set the interrupts and their priorities, and the graphics mode and refresh rate. Don't worry, I'll come back to set up some more necessary stuff here soon, but this last loop should be enough for the program to compile. Well, so long as I add in the proper cartridge header. I'm going to steal this Pokémon Mini cartridge header file from JVSTSX on GitHub, who created a clone of Death Planet for the Pokémon Mini written entirely in assembly. It looks really cool, but I don't know how to play it. The cartridge header needs to start with MN, then contain the vectors to the procedures for the many potential interrupt requests of the system, which aside from the startup function are all kept in a code section at the bottom of this file, and just returned from the interrupts since I'm not doing anything special with the timers or anything. The end of the header contains some sacred words, game code, and game name, followed by 18 bytes of 0. I don't think the emulators even check the header to make sure the header values are in the correct positions or contain the right magic words, but since I'm going to be running this game on hardware later, I'm gonna set it all up properly. Finally, I'll assemble and link this program using the S1C88 tools from earlier, and run my first Pokémon Mini program. Ah, a blank program. Just the way I like it. Now it's just time to write the actual game, starting with the graphics. Unlike the Game Boy or NES, there isn't any dedicated VRAM in the system. Rather, the console's graphics buffer is just sitting there in RAM from address 1000 to 12FF. You can directly edit the buffer if you want to, and even some commercial games do that. But the system is also set up with a separate background and sprite layer in one of the simplest graphics stacks that I've ever seen on a Nintendo console. Though granted, the most complex I've seen at this point is 1990's SNES. Even though the console's output display is only 96 by 64, there are 4 possible background tile map sizes: 12 by 16, 16 by 12, 24 by 8, and 24 by 16. This tile map is stored in RAM from address 1360 onward, with the rest of RAM after that being free for general use. Each entry in the tile map is 1 byte representing the tile offset from the start of the address found in the 3 map tile base registers. Each of these 256 background tiles are made of 8 bytes. Since the LCD is monochrome, each byte can be visualized as a vertical strip with each 1 bit representing a black pixel and each 0 bit a white or blank pixel. Normally, I use YYCHR for creating graphics for old Nintendo consoles, but since the Pokémon Mini tiles use vertical strips, I had to create my own graphics editor, which I've made public at my website, notin.tokyo/pminitiles. I've already created quite a few tiles as seen on the left, and it's almost too easy to select a tile from this group, then use the right canvas to edit it into what I need. Hitting the export button will download the data as a raw binary file, and you can see if I open it in YYCHR that everything is indeed rotated as it interprets the vertical strips as horizontal strips. Unfortunately, I just can't import the raw binary file into the assembly code like I could if I was using CC65, so I whipped up a quick little Python script that will convert the raw bytes into an include file that I can then include into the ROM at the specified address. I need the address to be explicit in this case, as it has to be copied into the 3 map tile base registers. And coming back to the PRC control register here, I've set the map size to 12 by 16 and then enabled frame copy, sprites, and the background layer. The last bit I didn't enable since it inverts the background layer. Then, as a little test, I'm just going to set up the tile map to follow the tiles from A0 onward, just to see if everything is actually working. And at this point, it's probably going to have a proper frame timer, so I won't be constantly going through my main game loop. I'm just going to write a simple loop here which will wait for the PRC counter register to change, which increases 65 times a frame, so it should run through the game code about twice for every frame, since the other registers are set up so the system runs at 36 FPS. This probably isn't the ideal way to time everything, but hopefully it shouldn't break anything down the line. And finally, I'm going to create a batch file to run the graphics conversion script, assemble, link, run, and then delete the program. Just a little automation so that in the future I can replace the graphics file without having to manually convert it to an include file again, and it'll delete the program afterwards so that in the case the next compilation fails, it won't just boot up the last working version of the program, causing me to be confused as to why nothing has changed. Perfect. For the game, I'm going to be building a version of Infinite Frogger. The Pokemon will cross the road dodging cars and skipping over lily pads. It's pretty cool to design games with such limited size constraints. For the 96 by 64 screen, I'll break it into 4 rows and randomly assign it to be either a dirt path, road, or river using a linear feedback shift register for the random value, and another procedure to write the background tiles to the tile map. Technically, there are actually 5 rows with 1 off screen, but that'll come into view as the player moves down. I've also added some code to switch the tile index of the river rows to add a flowing animation. It's done really simply by having the dashes move over 1 pixel to the right so that after 8 cycles the dash is back in the original position, but in a long row it looks like flowing water. The area between memory address 1300 and 1360 is the sprite object attribute memory, with one object being defined by 4 bytes representing the sprite's X position and Y position, both offset by -16 pixels, sprite tile number, and attributes, in this case being enabled, inverted, vertical, and horizontal flip. Notice how this leaves a couple of attribute bits unused, just like the sprites in the original Game Boy. Was Nintendo thinking about a potential sequel, the Pokémon Mini Color? As for the sprite tiles themselves, these are a bit different from the 8x8 background tiles. Sprites are 16 by 16, and there's an additional mask layer to the sprites that makes only that area visible. This way, the sprites can move over the background layer and only the masked pixels will be rendered while everything outside is skipped. In my tile editor, I can switch to view the 256 sprites on the left, and the canvas on the right can be used to draw the sprite graphics. All the black and white pixels contribute to the mask, so any blue pixels represent transparency. Then when I click Export Tile Sheet again, the program converts all these sprites into the proper format of a series of 8x8 mask tiles and graphics tiles in the proper order expected by the Pokémon Mini, and appends that to the end of the same binary file, which I can simply drop in as a replacement into the working folder. According to the size of the background tile graphics, the sprite graphics data should begin at 5800, so I can set that address in the sprite tile base registers. I'll set up the first sprite here as well. Keep in mind these sprites are rendered in reverse painter's order, so the first sprite in the OAM section will render on top of the rest. With the negative 16 pixel offset, this should set the Bulbasaur sprite to the top center of the screen. I definitely think the black outline was a good choice. By the way, I didn't draw these Pokemon, the graphics are from Luzi over on X the Everything app. I've chosen 8 of his designs to include in this game, just some of my favorite Pokemon, but go follow him. Of course, he does admit that he's a Digimon lover, so you don't have to if that makes you uncomfortable. Given the OAM size, there are only 24 sprites supported by the Pokémon Mini, so the first will obviously be the player, and for the next 20 I'm gonna dedicate to the on-screen moving objects. These objects will randomly spawn in, then afterwards I'll just move them horizontally by increasing or decreasing their X position in OAM until they hit 0 or 112 pixels. As a bit of a shortcut, when I'm looking for an inactive sprite slot to use, I just check if the X value is set to 0 or not. So I don't even have to do any manual checks to disable the objects going left, they just shut down automatically when they hit the edge. There's a couple of things to keep in mind with random spawns like this. Obviously there needs to be a cooldown period so objects don't overlap each other, but they should also be dense enough to pose a challenge to dodging. I think I got the spawn rate more or less dialed in, though I can always go back and make some adjustments later if it winds up being too easy. The Pokémon Mini also has an exceedingly simple way to read the user's controller input. It's all in a single register. The buttons are 0 active, so 1 is not being pressed. I'm only checking the D-pad here since all I need is a direction so I can set up the variables I need for automatic movement. My original idea was for the Pokemon to be restricted to a 5x4 grid, cutting off a little of the screen on each side so that the player can be perfectly centered on startup. Then the Pokemon would slide around from one grid position to the next. However, it dawned on me that if the player is going to smoothly surf on and off the top of lily pads, that's going to mess up my perfect grid. So I'm going to keep the automatic movement of the 16 pixels in a direction at a time, but not restrict it to a perfectly centered grid, so the player can go up to the left, right, and top edges of the screen, and once they try to get down to the third line, the entire background and all the sprites will scroll up. This shift is accomplished by increasing the Y-map offset register so that the 5th row comes into view. While I could have given every row in the tile map a unique row type and just scrolled through them all, I took a bit of a shortcut and once the screen has been scrolled a full 16 pixels, shift the row tiles back 16 pixels, reset the scroll to 0, and randomly assign a new row type to the 5th row. Don't tell me that I should have just rotated through the entire tile map, because the map does not roll over once the scroll goes beyond the map borders, so I'm doing it the right way. As for the trucks and lily pads, I also adjust their Y position in tandem with the background moving up, but once they've spawned they don't actually care what their Y position is, they just move left or right until they're out of sight, so it's no trouble for them. With such a tiny screen and being restricted to just a single background layer, there isn't a lot of room for a HUD. In fact, there isn't any room at all. But I'm still going to add in a score counter on the top right. Each time the player goes down a row, I'll increase the score by 1. This increased score procedure actually does a couple of interesting things. I start by adjusting the system control register to set the decimal mode and unpacked flags to on. This makes the ALU perform 4-bit BCD arithmetic, so each byte in the score array has a value only between 0 and 9. Then to output these values to the screen, I just add a 0 to that value and place it in the tile map from the first row's right hand side onto the left. Why are there 5 digits? Is anyone really going to play this game to 100,000 points? Well, originally it was 6 digits, but I didn't like the look of it taking up half the screen. As for interacting with the trucks, the players and trucks' hitboxes are a wee bit smaller than the full 16 by 16 square. To see if they hit each other, it's a simple 2D collision check that ends with the player exploding, I guess would be the right term here. After that sequence, the program jumps not to the reset vector, but a little way afterwards, because I want to preserve not only the high score in RAM, but also the current state of the random seed, otherwise every playthrough will be exactly the same. Interacting with the lily pads is quite the opposite. If the two object hitboxes line up, the lily pad snaps the first sprite to overlap with it exactly. And actually, that's all I have to do. Since the game engine moves the lily pad automatically toward its destination, as long as the player isn't moving up or down where I don't check for collision, these two hitboxes are still overlapping, so the player continues to get snapped along wherever the lily pad moves to. Of course, if they go off the screen, then back to the start. During the time they overlap, I set a variable called onLilyPad to true, which saves the player's life on the river. If the Pokemon enters a river row and the variable is still false, then after a few ticks, into the water they go. That's a restart. Up until now, I've been doing all my testing through emulation, which is great. I'm glad I get to play the whole library of Pokemon minigames on my PC, but I do own a Pokemon Mini, and since I have the hardware, I want to play my game on the real thing. As it happens, in the past year, there have been a whole slew of innovations for Pokemon Mini flashcards, mainly coming from an open source design from ZW Energy. His design is to use a Raspberry Pi Zero from Waveshare to act as the ROM chip, and honestly, it's a brilliant design. And since the Raspberry Pi Zero itself is just a few components to bridge together a Raspberry Pi 2040 microcontroller, Giltessa created this version of the Pi Zero and Pokemon Mini Edge connector all in one board that he calls the P-Mini flashcard that he sells on his shop online. But there's no reason why I can't stick with the original ZW Energy version of the board since I want to put it together myself. I'm going to use longtime channel partner PCBWay to manufacture these boards. Specifically, I need them exactly 1mm thick with an immersion gold surface finish, important since the board will be placed in and out of the console slot. I went with a black solder mask this time, just for fun. First time trying out a different color, and they look great, though I am very tempted to go with a transparent solder mask next time. Special thanks to PCBWay for sponsoring this project. I've personally used their services for all kind of manufacturing, from flexible PCBs to CNC to assembling entire designs. PCBWay has helped me out on dozens of projects, and they've never let me down. Check out the link down below for a discount on your first order. Again, super glad I went with the black mask this time. It really makes the gold stand out. And luckily, there are only 3 components I need to solder. The Pi Zero from Waveshare, I keep mentioning where it's from because apparently that's important, you don't want to fake one of these, and 2 100 kilo ohm resistors. These are 805, so not too small, but definitely at the edge of what I can do with my soldering iron. At least I can excuse my fairly rough looking soldering job here and the fact that I'm doing it with a camera between my arms and the smoke going right into my face. So you can laugh at me if you want, but I'm just happy I didn't mess anything up. I only bought a single Pi Zero for this. And with all the edges soldered on here, everything should be good to go. From ZW Energy's repository, there's an online patcher where I just upload the UF2 file from the releases page, along with the game ROM, and then I get a new UF2 file, which I just have to copy onto the Pi Zero, and then this cartridge should be good to go. You can see it's a really elegant design, really not a lot of differences between this and a standard cartridge. The Pi Zero is just filling in for the ROM. I've also printed the case from the repo and added a nice Inkbox logo just for good measure. And that's it. It's time to see this on real hardware. Hello? Oh no, that's not a good sign.
Who's that Pokémon? It's
Basic literacy. After a brief review of the README, I missed that I was actually supposed to also solder these contact pads on the back. So I'll just fill these in. I also reflowed everything on the front just in case, so this should be it this time. I love seeing a project come to fruition. This is Pokémon Mini Ambulation, with a whole roster of selectable characters from the first few generations. It's quite a fun mini-game, suitable for a mini console, and there's no better feeling than seeing my own game come to life on real hardware. I've really fallen in love with the Pokemon Mini, but I think the main problem with the system is that it's mini. It looks like a toy when really it's a fully fledged mini Game Boy. The other problem is, it's too niche. I know, right? Part of the world's largest media franchise and still too niche. But if they had called it the Game Boy Mini or the Nintendo Mini and had some Kirby mini games, or how about a version of Donkey Kong or some WarioWare? This thing is screaming for some WarioWare. They already have a purple version of this console that no one ever bought. There's no reason why they couldn't have done that. Honestly, it would have been the perfect first console for kids just getting into games. It's just an absolute tragedy that the system didn't catch on. My parents wound up getting me one of those round 20 questions balls instead. And actually, it wasn't even mine, it was my sister's. The homebrew scene for this console has to be one of the most dedicated I've ever seen. Seriously, people are pushing this hardware to the absolute limits. It's pretty cool what they've been doing. If you're interested in Pokémon Mini development, now's the time to get going with it. The Pokémon Mini has a special place in my heart. I'd secretly been obsessed with this console for quite a long time, so I'm glad I finally get a chance to share just how amazing this little machine is. The only one gripe I have with it? Why is there no volume control? Are you kidding me? This is why parents didn't want to buy it. Who wants a toy for their kids that's constantly beeping every time they turn it on? There you go, Nintendo. I solved the whole reason this was a commercial failure for you.